Okay, folks, learning goal 3. This one will be pretty short. Be familiar with black body radiation. So we're not going to go into the full nitty-gritty details. So that's why the learning goal just says be familiar. Okay, let's navigate to the slide and let's go for it. So a couple of postulates. Number one, all objects above 0 Kelvin emit thermal radiation. The energy of that thermal radiation is proportional to the temperature of that object. An ideal emitter of thermal radiation is called a black body. So not all emitters are ideal, but that's what we call the ideal emitter. And the black body radiators will follow the Planck distribution. So there's some nasty math here that we want to familiarize ourselves with. So first of all, we can see here, if we were to look at a graph of this Planck distribution, where we have energy distribution on the y-axis and wavelength on the x-axis, you can see here it follows this Boltzmann-like distribution. And so if we were to integrate the curve under that Boltzmann distribution, as noted here, that would give us the total energy of the radiator. So now I want to point out this exponential that's in the denominator of the equation there. And again, I mentioned I'm not going to go into full details how this is derived, but I do want you to notice that there is a partition function going on there. So if you recall from last semester, partition functions follow this general form of exponential to the negative energy, or usually just to energy divided by K Boltzmann T. Okay. So the negative sign doesn't necessarily always have to be in there. So we'll just leave it as energy divided by K Boltzmann T. So now if we inspect this really closely, you can see we've got exponential of HC over lambda divided by KBT. So that HC over lambda, right, that is our energy. So this is following this Boltzmann distribution, or this population of states. So to the right of me here, you can see I've got this really cool simulator that you can find with this link right here. And right now in this simulator, we're parked at the temperature of the sun, about 6,000 Kelvin. And so if I turn that temperature down, you can see here that not only does the distribution go down as far as the power, so how much total energy is emitted, but it's also shifting out to more and more red wavelengths. And if I get to something like the temperature of a light bulb at about 3,000 Kelvin, you can see the distribution has gotten quite small. So I've got to zoom way in there. And you can still see it's emitting some visible light, but now the peak of that distribution is in the infrared. And if I bring that temperature down even further into like Earth-like temperatures, maybe let's go something like room temperature, like 300 Kelvin. We can't even see it on this scale, right? I have to zoom way in to see it. And there you can see just the tail end of that sucker. I got to zoom way in now to the infrared. And so this makes sense, right? The Earth is an object that glows in the infrared. Or we, humans at about 310 Kelvin glow in the infrared. Okay. So that's all that I wanted to talk about for black body radiation for the time being.